All right, let's pick up where we left off last time, talking about these orbitals and sublevels and shapes. Just to kind of clarify what we were going over previously, we have the principal quantum number, the angular, and the magnetic. And just again to say what these guys are, this is just the row on the periodic table. So whatever the n number is, that's the row you're in, and it's an energy level. Within each energy level, you have a certain number of sub-levels. Let's go ahead and write that in here so we can see that. Sub-levels within the main energy level. So energy level 1 has only one sub-level, the S. Energy level 2 has two options, the S and the P. Energy level 3 has three options. And energy level 4 has four options. And I'll drag over a periodic table and we can actually look at that. So our handy dandy periodic table doesn't actually label the energy levels, so I'll just go ahead and write them in. 1, 2, 3, 4, 5, 6, 7. All right, this is as good a time as any to talk about how we can eventually do electron configuration, which we'll get to later on. But this energy level 1, as we're going across, we have two elements, and these guys are both designated to the S block, even though this is the end of the S block right here. So hydrogen and helium are both in the S block. They both are found in, or have electrons, found within the S sub level. Energy level 2 also has some S block elements. There they are. And then if you slide on over, these 6 elements in a row are all part of the P sub-level. So row 2 has an S and a P sub-level. This gets a little weird. Energy level 3 only appears to have 2, just like 2 did. So it's got the S, it's got the P, but these guys here all are actually found, that's supposed to be an arrow, one row higher as far as their energy level goes. So row 3 has the S, it has a D for these guys, and there's 10 of them, and then back to 6 for the P. Row 4 has an S, these guys, has a D and a P, and then when you get to 5, this is where it gets a little bit screwy. When you get to 5, you have your S, you've got your D, but then you also have these guys, which are found in row 6. So this is actually found, whoops, well, where they fit down here. Actually, I take that back. They fit right here, 58. So they fit right over here in this part of the periodic table. But their numbers, even though it's in row 6 and 7, they are, let's say, row -2. So this is actually, I don't know where I'd write it. I'll say 6 -2 and 7 -2. So it's actually a 4. And this would be a 5. So 7 -2, pull this up a little bit. 7 -2 would make it a 5. So again, these guys are actually found over in here. So I'll continue this over in row 6. These are the S's. And then typically we kind of go and just start calling these guys the F's. We don't need to dig in too deep. So it would be 6 S's, and then this -2 would be 4 F's. And then this would be 5D, and then back to 6P going across. We'll play around with this later when we do some electron configuration things. Okay, let me push this aside and continue just a little bit. Actually, let's go ahead and do a homework problem. We'll look at number 53. Okay, and we'll swing the periodic table over here just to help us out in a little bit. Give the numerical values of N and L corresponding to each of the following orbital designations. Okay, so for 3, P is 3P, or how is that an option? So as far as the first number, this is the principal quantum number. So we're thinking N. What would N be equal to? So I think that's going to be 3. That's not too bad. And then for the L number, remember what we had for our L's, and I'll pull that item back over here. So for our L numbers, we had these corresponding values that went along with them. So if we're looking, saying, okay, so for P, what is P going to be equal to? P looks like it's equal to 1. Okay, so L for this P is simply 1. Okay, 2, that one again is easy. It just is 2. And for the S was the first available number, but according to our sheet here, when we have an S is equal to 0. Takes a little bit to kind of catch on to this, but eventually I think we're okay. This one, N is equal to 4. And L, okay, for 4, what is that going to be? We only had an example or two of that. So that was going to be 3 for that one. 3. And then for D, guess that's the one we don't have so far. L will be equal to 2. So to summarize those values that we had, let's say assigning quantum numbers. N can be anything 1 through 7. L can be 0 all the way through N minus 1, whatever N happened to be. It can be as high as that, N minus 1. And then the next one, I didn't write this down. It's actually called M, the magnetic, M sub L. It can be as large as negative L, or as small, excuse me, all the way through positive L. Now there is a fourth quantum number, and I'm going to write that down here. So M, magnetic spin number. We'll talk about this a little bit more, but I'm just going to get it out of the way. For any fourth number, you have 2 options. And this will fit in later. I'm just kind of getting this out of the way. Positive 1/2 or minus 1/2. And that's called its spin, because you can put 2 electrons within each orbital, and they have to have opposite spins to minimize repulsion from each other. But we'll see how this is going to play out a little bit later on. Okay. Let's start off with a little bit more notes, and then we can go from there. A little bit more about electrons. Electrons that are found in the same sublevel. In other words, the S or the P or the D, not all of them together, but all the S's, the electrons that are found there, all the electrons found in the P or the D. So the ones that are found in the same sublevel have the same energy. So for example, all electrons in the 3D orbitals. But the sublevels are not the same energy. So in other words, S, or I'll say 3S is not equal to 3D. Those are different. different amounts of energy. All the S's are the same, all the D's are the same, but those two guys are not the same. All right, we'll finish it here and I'll draw a diagram for our next lecture.